Section 3.7, Optimization Problems. So the methods we've learned so far in this chapter for finding extreme values have practical applications in many areas. So what we're going to be doing in this section is we're going to try to employ methods that we've learned in this chapter to tackle such problems. All right, so let's consider the following situation, example 1 that you see on the screen. A farmer has 3,200 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. Okay. He's not gonna fence the river, the riverside. So he's gonna need no fence at all along the river. The question is, what are the dimensions of the field that has the largest area? And that field is a rectangular field, right? So the situation is as follows. You have a river. So the farmer has a river. Okay, let's color it in blue. So that's the river part. And the assumption is that this is a straight river, right? So that's the river part. And what he's gonna do is he's gonna try to fence off a rectangular area which is gonna be bordered by the straight river, right? So the straight river is gonna be one of the sides of that rectangular field that he wants to fence off, right? So he's gonna have to fence an area like this, rectangular area like this. One side of which is the river, and he's not gonna use the fencing he has on that side. Okay, so only the orange or the brown part that you see on the screen is what he's gonna be fencing. Correct? All right. The question is, what are the dimensions of the largest area that he can fence? All right, so to tackle this question, how about we give ourselves a context, symbols to denote the dimensions of such an area or such a geometrical shape, which is rectangular in this case. How about we give ourselves the label A for one of the sides, and let's say this common side is A, right? The length. The two sides have a common length, which is A, and the other side is B, right? Because it's a rectangle. So these have to be the same. Okay. Very good. And what do you know about A and B? What type of constraint you should put on A and B? Well, you know that the fencing that he has is only 3,200 feet, right? So, and he's gonna use it to come up with this circumference in some sense, right? With this brown thing that you see on the picture. So what we can say then is that A plus B plus A must exhaust the 3,200, right? So A plus B plus A should be that 3,200 of fencing that he has. Okay, so I'm gonna write this down. So A plus B plus another A, which means 2A, should be 3,200 feet. Make sense? All right, and what is he trying to do? He's trying to, or the question is, what's the largest area, or what are the dimensions of the largest area that he can fence off? Correct? So we want to maximize, they're talking about the largest area, we want to maximize the area function of this geometrical form, right? So what's the area function of this shape? Let's call it calligraphic A, the area of this rectangle, right? The area of this is A times B, correct? And A is this measure, and B is this measure. As such, this function A is a function of two variables, little a and little b. But we haven't studied, we're studying single variable calculus. We don't know how to maximize a function of two variables. So what we're going to do is we're going to ask or try to explore a relationship between A and B so that we can rewrite this whole product as an expression just in one variable. So that calligraphic A, the function calligraphic A, becomes a function of one variable. Okay? So what type of relationship exists between A and B? Well, it's already here in brown. 2A plus B is 3200. So you can relate A and B via this relationship. So this guy gives me, let's say, B is 3200 minus 2A, right? So if you want to call this asterisk, because of asterisk, you can say that this area function is equal to A times 3200 minus 2A. Make sense? Because B is 3200 minus 2A if you solve for B in the asterisk equation. So you get this. So now A can be seen as a function in one variable. And that variable is little a. Correct? So we get A as a function of little a, right? All right, so what's the question? I want to find the dimensions of the field which has the largest area given that 3200, right? So we've already used that information. So we want to find for what numbers, little a and little b, calligraphic A, the area function, is reaching its maximum. All right? All right, so we're going to maximize. So our goal is to maximize calligraphic A. Very good. Quick question here. So what can you say about little a? What type of constraints should be placed on little a? Well, little a is certainly non-negative, right? So little a is certainly non-negative. Why? Because it's a measure, right? It's the length of this side. So this guy cannot be less than 0. On the other hand, the area cannot be negative. The area function cannot be negative. And the area function is negative. Given that little a is non-negative, the area function becomes negative if little a exceeds 1600, right? So one more time. We know that little a should not be less than 0. So it should be non-negative. As such, this guy here is non-negative. Now, calligraphic A, which is the area of that rectangular thing, cannot be less than 0, right? And this area is less than 0 if this guy now is less than 0. And this guy is less than 0 if you unravel what this means. This guy is less than 0 if A is greater than 1600. Correct? Since you don't want it to be less than 0, so the largest value for A is 1600. So we're going to maximize this function, the calligraphic function A, on this interval, which is a closed and bounded interval, right? As such, by the extreme value theorem, we know that this function is going to attain a maximum, an absolute maximum inside, right? Okay. The question is, to which little a that maximum value correspond to? So we are after that. We know that thing is, so we're looking for something that exists, okay? That's my point by the extreme value theorem. All right. So how can we go about this? Well, we're gonna differentiate calligraphic A, right? The function, the area function. So we're gonna differentiate calligraphic A with respect to little a, right? This means we're differentiating with respect to little a that function capital A, right? Or calligraphic A. Make sense? All right, and what is this? If we differentiate this, this is, I mean, you use whatever you want. This is 3208 minus 2a squared, right? Or you can use product rule here. Whichever you use, you're gonna get 3200 minus 4a, right? All right. And the critical numbers, what are the critical numbers here? The critical values of this function calligraphic A. Well, we don't have critical numbers of type 2, right? Because the domain of A prime remains that thing, 0 to 1600. So the only critical numbers we're gonna pick up for A are those which are gonna allow A prime to vanish, correct? So we're gonna see where this vanishes, and this vanishes as long as A is what? 3200 divided by 4, which is 800. Makes sense? So A prime is 0 if and only if little a is 800. All right. And now if you create this table of variations that we talked about, if you try to do that, the table of variations, so you're gonna have, let's do it quickly, why not? So our interval is what? 0 to 1600 here, right? And 800 happens to be a critical point. Okay. So at this point 800, the derivative of A vanishes, correct? And this first row is where little a lives, right? Okay, and before that, the function A prime is gonna preserve a sign, one sign. And if you take a point between 0 and 800, whatever point you take, you plug it in A prime, you're gonna get a positive entity, right? So that thing is gonna be positive. And over here, after 800 to 1600, if you take whatever you take, that thing is gonna be negative. So what can you say about A? What can you say about A by the first derivative test? What can be said about A is that at 800, the function calligraphic A is gonna attain a local maximum, right? Because the function A prime is switching signs from positive to negative, correct? So since A is increasing here and then it's decreasing there, by the first derivative test, I know for sure that the function calligraphic A is attaining a local maximum over here, right? Make sense? And this local maximum, since it's increasing before and decreasing after, and this is actually the interval 0, 1600, all of the interval, right? Remember? So calligraphic A has the following constraint. Its input little a cannot drop below 0 and cannot exceed 1600. So apparently this is going to be the global or the absolute maximum on 0, 1600. Make sense? All right, if you don't see it this way, how about we invoke what we refer to as the closed and bounded interval method. So we're gonna evaluate the function A at 800. We're gonna evaluate calligraphic A at 0 and at 1600, at the endpoints and the critical points, correct? So in this case, the only critical point is 800, and the endpoints are 0 and 1600. So we're gonna evaluate A at those 3 points, and find out that this is actually the maximum that we're talking about, the absolute maximum here. Okay. So another approach is to use the what did we call it? A closed and bounded interval method, right? So if you evaluate a at 0, and if you evaluate a at 1600, you're gonna find 0 here, right? Let's check it again. So a at 0, if you replace little a by 0, this whole thing is going to be 0 because this guy is 0. One of the factors is 0. And if you replace little a by 1600, that guy is going to be 3200, and 3200 minus itself is 0. So this factor is going to be 0, so the area is going to be 0. So you're going to get 0. And so a at 800, it's going to get a positive entity, and hence that's going to be the maximum. And it's going to be the absolute maximum on 0, 1600, right? And what's that value? A of 800. Well, so we're going to replace little a by 800. So I'm going to get 800 times 3200 minus 2 times little a. So 2 times 800 is 1600. Am I correct? Okay. And what's this value? What's this value? This is equal to 800 times 1600, and this is equal to 128 times 10 to power 4, right? To be honest, I don't care what this number is. I only care that this is bigger than 0, correct? Why? Because by the closed and bounded interval method, whichever is the highest among all three values, a0, a at 0, a at 1600, and a at 800, is going to be the absolute maximum, correct? So I don't care what this number is, as long as it's beyond 0, it's bigger than this value, correct? So this means that the maximum, that local maximum, is actually the absolute maximum in between 0 and 1600. Okay, so this is the maximum value. So a of 800 is the maximum value of the function a, okay, on the interval 0, 1600. All right. Okay, but this is not the question. The question is, find the dimensions of the field which has the largest area. We know now when that area happens, the largest area. It happens when little a is 800, right? So when little a is 800, so little a has to be 800, so that the area is reaching its maximum of the rectangular field. So one of the dimensions they're talking about is known, right? At this point. So little a is known, it has to be 800. Now the question is, what should b be? Well, b and a are related via this recipe. Twice a plus b should be 3200. So asterisk is going to actually reveal to us what b is. All right. So now by little b here, and by equation asterisk, we infer that b has to be 3200 minus twice the a, right? And what's twice a? Well, twice a is, what's a? A is 1600, right? The a we're talking about is 800. So 3200 minus 2 times a, and a is 800, so this is 1600, right? 2 times a is 1600, and this is 1600. So what can you say then? We can say at this point that the largest area occurs when little a is 800 and little b, because b has to verify asterisk, and little b is 1600. Make sense? So the conclusion is the rectangular field should be 800 feet deep, right? And 1600 feet wide. Make sense? So it should be 800 feet deep and 1600 feet wide. All right. So this is the end of the first problem. Let's move on to the next one. All right. So find the area of the largest rectangle that can be inscribed in a semicircle of a fixed radius r. So r is chosen, right? So the question is, what's the largest rectangle that can be placed within that semicircle, which means two of its vertices are going to be on the semicircle. Okay. So let's say I have a semicircle like this, and that thing has radius r. The question is, they want to inscribe here a rectangle, right? And the question is, what's the largest rectangular form that we can inscribe inside that circle? Okay. Well, for simplicity, I want to assume that the circle is an upper half circle first, and centered at the origin of the Cartesian coordinate system. Okay, so I'm going to assume that it's centered exactly at the center, at the origin. Okay, so this is the origin 0, 0. Okay, all right, and I'm talking about the upper half circle. So things become, the y values are positive, just for simplicity of to simplify matters in terms of calculations. Okay. All right, so let's give ourselves a context. We would like to maximize something, right? I want to find the largest area. So I want to maximize the area function. Okay. So in order to find the area of that rectangle, how about we give ourselves a context? We label the sides of this rectangle. How about taking this point to be, one of the vertices to be of coordinates x comma y. Okay. What's the relationship between x and y? X and y, this point, x and y are the coordinates of this point, and this point belongs to the circumference of that semicircle, right? And what's the equation of the semicircle? This is x2 plus y2 equals r squared, right? But you know more than this. If you solve for y, you get y equals plus or minus the square root of r2 minus x2. Am I correct? But certainly y is a positive thing, so you throw away the minus sign. Makes sense? So I'm going to erase the second part because it's implied by the other one. Okay. So one more time, given that we've chosen an upper half semicircle, then we're talking about y being positive, and as such, the equation that I just erased is equivalent to this. Okay. All right. And now, what can you know about? What can you say about the length of these sides? Who's x? Who's y? Over here. So this height is y, right? This height is y because this is the height of the point. So this height is y. And this guy is x, right? This guy over here is x. So this guy over here is simply x. But we're taking the center of that semicircle to be the origin, so the y-axis is an axis of symmetry of that semicircle. So as such, this is also an x. Correct? So this is also an x. So what can we say about the whole thing then? So about this whole thing. So this whole thing is twice x. Makes sense? Okay. All right. So what's the area then of that rectangle? What's this area here? This area over here. How about we call it calligraphic A one more time? Okay, so calligraphic A one more time. So calligraphic A is equal to y times 2x, right? 2x times y. So 2x times y. So length times width, right? Y times this measure, which is 2x. That's the area of that rectangle. All right, but once again, as in example 1, this is a function in two variables. I want to try to find a relationship between x and y, so I can turn this expression into an expression in one variable so that a becomes a function of one variable. So I can deal with it given the knowledge I have so far. But it's already established, right? The relationship between y and x. Y is this much of x. That's the function, that's the relationship between y and x. So if you replace y by this much over here in the a function, the area function, you can make the area function a single variable function, okay, in x. So as such, a is a function of x, to be precise. Let's say 2x times y, but y is r square root of r squared minus x squared. Okay. And what we want to do is we want to maximize that thing. We want to find when that thing, or what is the largest value that a can reach. All right. What type of constraints do you have on the variable of this function calligraphic a? Well, the variable is x, and x is a measure, so certainly cannot drop below 0. So x cannot drop below 0, so it's non-negative. And x should be chosen so that this radicand cannot be negative, right? Because if the radicand is negative, the square root doesn't make sense, and hence the area function doesn't make sense. It's not meaningful. So if you try to understand when r squared minus x squared is non-negative, that happens when x is between minus r and r, correct? And since x cannot drop below 0, the largest it can reach is r. Okay. So the largest it can reach is r. So I want to maximize calligraphic a given that x is bounded below by 0 and bounded above by r. All right, makes sense? So how we're gonna start? Well, by the extreme value theorem, we know that a is gonna attain an absolute maximum on 0r, because 0r, this interval, is closed and bounded. So I'm gonna be looking for something that exists. All right, and how are we gonna find that value where a is gonna attain its absolute maximum? Well, I'm gonna find the critical points of a, the critical numbers of calligraphic a, and then I'm gonna evaluate calligraphic a at those critical numbers and at the lower and upper endpoints of the interval 0 and r, and by the closed and bounded interval method that we learned a few sections earlier, I'm gonna be able to deduce what value is the absolute maximum. Okay. All right. So I'm gonna differentiate calligraphic A. And if you differentiate calligraphic A with respect to x, how about we do product rule? So 2 times the square root of r squared minus x squared plus 2x times the derivative of square root of r squared minus x squared. I'm going to use the chain rule for this. So chain rule for this is going to give us a negative 2x times 1/2 the square root of r squared minus x squared, right? So what did we use here? Chain rule, but obviously not only chain rule. I also implicitly meant the power rule, right? Because this can be thought of as r squared minus x squared to power half. All right, so we get this. Let's do the same denominator. Let's do the same denominator, which is 2 square root of, oh, by the way, this 2 and this 2 can cancel each other, right? So let's cancel it before we actually make the same denominator. So we cancel this guy with this guy. And let's erase that, so we don't need that to be part of the denominator. It's already cancelled. And what I get is denominator being square root of r squared minus x squared. Okay. And over here, to make the denominator here square root of r squared minus x squared, I want to multiply also above, the numerator by square root of r squared minus x squared. And this times itself becomes r squared minus x squared, right? So that becomes 2 times r squared minus x squared minus the x squared minus this x squared, right? So one more time, how did I get this? I created a denominator which is square root of r squared minus x squared. And if you want to create that denominator downstairs, you also have to multiply this expression by square root of r squared minus x squared. But if you multiply this expression by square root of r squared minus x squared, this guy becomes, it loses its umbrella, right? You're squaring the umbrella of this expression, so no more umbrella. We get this. And this x squared comes from x times x. Oh, I forgot the 2, right? So there is a 2 here. So 2 times x is 2x squared with this minus. That's going to dominate the plus, right? Okay. All right. So this means 2r squared. So this means upstairs 2r squared minus 2x squared minus 2x squared is minus 4x squared. So minus 4x squared. Am I correct? And minus 4x squared, if you factor out 2 over here, so that guy is going to be divided by 2. Correct? If we factor out 2 here, we get something like this. And that denominator remains the same. R squared, square root of r squared minus x squared. Agree? All right. So what are the critical number of A? Remember A, it was defined on 0R. What are the critical numbers? There are points here which are of type 2. I lost R along the way, right? So I know that R is in the domain of the function A, but not in the domain of the function A prime. Agree with me? Because if x is R, this expression doesn't make sense, because downstairs would be 0 and A prime would be non-meaningful, so it doesn't exist. So since R is part of the domain of A, it was in the domain of A, but not in the domain of A prime, then R is a critical point. CP for critical point. Okay. What are or what is the other critical point? Well, there are those points which allow A prime to vanish. And A prime vanishes. What's A prime? A prime is this quotient, right? A prime vanishes if this quantity between the parentheses is 0. So the other types, or the other type of critical point, come from the fact that a prime is 0, and this happens precisely if this numerator is 0, and the numerator is 0 if r squared is equal to 2x squared, right? So if r squared minus 2x squared is 0, which if you solve for x, you should get x squared equals r squared over 2, right? Which means x is plus or minus square root of r squared. What's square root of r squared? R is positive. It's r divided by square root of 2. Makes sense? So we get this. Okay. All right. So x is equal to that. So x is equal to that. Well, the negative part, I mean, certainly this quotient is positive. Since x cannot be less than 0, this negative part is to be rejected. Correct? This negative part is not part of the domain. Negative r divided by square root of 2 is not part of the domain. So the only other critical number other than r is plus r over square root of 2. And certainly this number is smaller than r, because 1 over square root of 2 is less than 1. So this guy is part of the domain. It's part of our domain, which is 0r, right? Okay, so this is another critical point. So this is another critical point. So it's also a critical point. Right? So, I mean, again, there are many ways to end it. How about employing, because we've done it in a different way above, how about we employ the closed and bounded interval method, which means we evaluate a at this critical number. I'm going to highlight them for you. At this one, at this one, okay, maybe I'll highlight this one, right? So these are the critical numbers, and I want to evaluate a at the endpoints. What are the endpoints? 0 and r, right? So at this and at this. Makes sense? So I'm going to evaluate a at 0, r, that's another time, so you don't have to do it twice, obviously, it's the same, and this guy. Makes sense? And whichever is the highest is going to be the maximum value that a can take. So I'm going to evaluate a at the lower end point. I'm going to evaluate a at the upper end point. I'm going to evaluate a at the critical points, but one of the critical points is r. It's already, I mean, it's going to be here. And the other one is r over square root of 2, right? By the closed and bounded interval method, whichever is the highest is going to be the absolute maximum. And that's going to be, I mean, it's going to be the absolute, it's going to be the maximum value that calligraphic A can attain. All right, what's calligraphic A at 0? Calligraphic A at 0 is 0, right? 2 times 0 is 0 times a number, so 0. So this guy is 0. Same thing, if you evaluate a at r, also 0. The radicand is going to be 0 this time. And calligraphic a at r over square root of 2, at r over square root of 2, what was a again? It was this guy, right? So how about we copy this? So we copy this. Let me take it below so I can use it. So this is a of x, correct? This is a of x. So that's a of x. I just copied it just so I don't have to scroll up and plug in r over square root of 2 back and forth. All right, so I'm plugging in here, instead of x, I'm plugging in r over square root of 2. And what do I get? 2 times r over square root of 2. 2 times r over square root of 2 times the square root of r squared minus x squared, right? And what's x, my input? R over square root of 2. So I get this. Make sense? All right. Gonna erase this. I don't need it anymore. Okay. And what is that? What is this value? Certainly this value is positive, right? Certainly this value is positive. And hence it's going to be the maximum value that the function a can attain, because both of these guys are 0. So certainly this is going to dominate all 3 values. So the absolute value is whatever we're going to be writing next. Okay? All right. What's 2 times r over square root of 2? If you would like to rationalize the denominator, this is simply r times square root of 2. Correct? If you want to rationalize the denominator here, which means multiply downstairs and upstairs by square root of 2, as such, downstairs becomes 2, and 2 downstairs and 2 upstairs, this is a 1, times the square root of 2. So r times square root of 2 is upstairs, times square root of this guy. What's this guy? This is r squared minus r squared over 2. Agree with me? Because this guy squared is r squared over 2. All right, and r squared minus r squared over 2 is simply r squared over 2, right? So half minus 1 minus half is half. Okay, and this is what then? This is equal to what's square root of r squared divided by the square root of 2? This is r over square root of 2, right? This is r over square root of 2, this guy. Okay, and the square root of 2, and with this square root of 2 they cancel each other. So this guy times this piece becomes r times r, which is r squared. So which is r squared. Okay, and since r is positive, as we said, this is certainly a positive entity. This is the radius squared. Okay. All right, so what's the largest, question was the largest area, right? The largest area of a rectangle that can be inscribed in such a semicircle. Well, we found it to be r squared, and this happens when you take x. What's x? This measure, whenever you take this measure to be r over square root of 2. If you take this measure to be r over square root of 2, and you let y to be the square root of r squared minus x squared with that choice of x, create this rectangle, that's guaranteed to be the largest area that can be inscribed in such a semicircle with that radius, whatever that radius is. Make sense? Okay. So I'm gonna just summarize it by just saying here, before we move on to example 3, the largest area. So the largest area that can be inscribed in a semicircle having radius r is r squared. Okay. Finally, the last problem in this section. Find the point on the parabola y squared equals 2x that's closest to the point 1, 4. Before we start, actually, let me just make the following proposition. Suppose that you have a function that's non-negative on an interval I, which means f produces non-negative outputs for any input coming from I, with a number x naught to be in I. Okay, so this is an interval, and let's assume that x naught is inside I. Then the following are equivalent. F, the function f, attains its minimum at x naught if and only if the square of f, this is the square of f, is attaining its minimum at that number x naught. Okay, so let's actually prove this proposition. Let's prove this proposition. This is an if and only if statement, so it's a double implication. It's a two-way street, correct? So it's this way, it's this way, and it's this way. Correct? So it's a double implication, left to right implication and right to left implication. Let's start with this implication, which means that we are assuming that the function is attaining its minimum at x naught, and we want to show that the square of that function is also attaining its minimum at x naught. Okay, what does it mean that f is attaining its minimum at x naught? This means that, so we're gonna assume that f of x naught is less than or equal to f of any x, other x, coming from I, right? This is what it means for x naught or f to attain its minimum at x naught. Make sense? So it means f of x naught is the lowest value the function can reach on that interval I. Make sense? All right. And this is a non-negative number, right? This is certainly greater than or equal to 0. Why? By assumption. Since f is non-negative. Since f is non-negative on I. Right? So as such, if you square both sides, in other, what does it mean, square both sides? It means that apply the squaring function. Since the squaring function is increasing on 0 plus infinity, the inequality sign is not going to change, correct? So it implies, by applying the squaring function here, so we're applying the squaring function to both sides. I'm squaring both sides, that's what I mean. Squaring function. Right? So as we said, which is increasing on 0 plus infinity. So it's an increasing function on 0 plus infinity. So a smaller value corresponds to smaller output, right? So we get that the square of f of x squared, which means the output through the squaring function of this input, that's what this means, is less than or equal to the square of f of x. Which means what? Which means that, what does this mean? This means the output of the squaring function when the input is f of x, correct? And this, since this used to be for all x and I, this is gonna also be for all x and I. For all x and I, right? And what does this mean? Well, this means exactly what we want to show. We want to show that f, the square of f, attains its minimum at x naught. Look, read this. This doesn't mean that x naught is where f, the square function, is going to attain its minimum. because it's dominated by all other values that the square of f takes, correct? So we showed the right to left implication, the left to right implication, the brown one. Now we're gonna go with the green one. So right to left. Okay. You know what? How about I leave it as an exercise, but um, I wanna still just at least talk about it. So this guy is left as an exercise. Let's just at least talk about it. I mean, it's already on the screen anyway. If you assume this now, if you assume that the square of f is attaining its minimum at x naught, which means you're assuming this, right? You're assuming this. Okay? And this is a non-negative entity. This is a non-negative entity. If you apply the square root function, you want to kind of go back now, right? If you apply the square root function to both sides, square root of, which is an increasing function, square root of this is going to be less than or equal to square root of that, right? And what's the square root of something squared? It's the absolute value of the thing. So we're going to get absolute value of f of x naught is less than or equal to absolute value of f of x for all x and I. But what do you know about f? F is non-negative. F is non-negative. And what does this mean? Absolute value of f of x naught becomes f of x naught. So you go back, you're right there. F of x naught is going to be less than or equal to f of x for all x and I, and this means that f is going to attain its minimum at x naught. Okay? So this, the right to left implication, I left it as an exercise even though I said it, I mean, we discussed it. But the idea is, if you have a function that's non-negative on an interval, the result, I mean, I'm going to use the result. If the function f is non-negative on an interval, then if f attains its minimum somewhere on that interval, the square of f is going to attain its minimum at the same point. And vice versa. If the square of the function is attaining its minimum at some point on the interval I, then f is going to attain its minimum at that very same point. Okay? Under the assumption, don't forget, the assumption is f is non-negative. If f is non-negative, there are things which I could have not used along the way, right? I mean, given that we know the proof now. All right, back to the problem. Find the point on the parabola y squared equals 2x that's closest to the point 1, 4. Okay. So now back to the exercise. Back to example 3. So I have the parabola. How do you graph this parabola? Y squared equals 2x. It's something like this, right? This is y squared equals 2x. And what is the point 1, 4? 1, 4 is maybe here. That's 1, 4. Why it's right there? Why it's not below or above? Because what's this point? What's this point over here? What's this point on the graph whose first coordinate is 1? Well, if the first coordinate is 1, y squared is 2, right? One more time. This point, the blue point, belongs to the graph of this parabola given by this equation, y squared equals 2x. So the coordinates of this point are going to verify the equation, right? If the first coordinate is 1, so x is 1, if this guy is 1, the y value is how much? Y squared is 2, so y is going to be plus or minus square root of 2. Agree with me? So that guy is going to be 1, square root of 2. And this one here is the negative square root of 2, right? So 1 comma negative square root of 2. So for the x equals 1, it's going to generate 2 points on the parabola, namely 1 comma square root of 2 and 1 comma negative square root of 2. All right, my point was that point here, which has first coordinate 1 and second coordinate 4, is certainly bigger than square root of 2, right? Square root of 2 is smaller than 4, obviously, right? Because 2 is smaller than 16. Okay, that makes sense. All right, so so that green point should be above the graph. All right, let me erase all the last steps I did. All right, so we're here. The question now is, I want to find the closest point on this graph. I want to find the closest point on this graph. I don't know where, but the closest point on this graph to that green point, okay? To that green point, this one. So this point has coordinates 1 comma 4. So I want to find the closest point on the graph to that green point. All right. So please stop this video and try to come up with it on your own. And once you do so, let's keep going then. How about I label this point, which is a generic point on the curve y squared equals 2x. How about we call it x comma y? Okay. How about we call it x comma y? So x comma y belongs to the graph of that parabola, y squared equals 2x. And what's the distance separating the two? This is the distance separating the two, right? That's the distance separating the two. Let's call it little d. That distance, I would like to minimize it, right? This is the idea here. I want to minimize that function, little d. We want to minimize little d. And what's little d? Little d is the distance separating this generic point, the blue point, and the green point. And what's the distance separating 2 points on the plane? The Euclidean distance. It's the square root of the sum of the squares, right, of the differences between the coordinates. So the first coordinate of the first point, let's say x, the second is 1. So that guy is going to be here, x minus 1. And the second entity here is going to be the difference of the coordinates, which the second coordinates, so y and 4 in this case. Correct? All right, this is a function d in 2 variables, x and y. I would like to have a relationship between x and y so that I can turn the function d into a single variable function. So I can use the tools I learned so far. And what's the relationship between x and y? Well, the point belongs to the curve, right? Y squared equals 2x. So those coordinates have to verify this equation. So if you replace the blue x by, or if you replace the brown x by the blue x, and if you replace the blue y by the, or the y, the brown y with the blue y, okay, you should get a true statement. So then we get that the blue y squared should be twice the x, the blue x, which means x is 1/2 the blue y squared. Make sense? So this is the relationship then between x and y. Which x and which y I'm talking about? The x and y of the coordinates of this generic point that I took. Okay, so now replace that x, because this is the blue x, right? Replace that x by 1/2 y squared and turn this function into a single variable function. So this gets us to square root of So x is half y squared minus 1 squared plus y minus 4 squared, right? All right. And this is then a function in one variable, which is y. What do I want to do? I want to minimize d. We want to minimize d. To minimize d, right? Why we want to minimize d? If you forgot, this is the question. This is the question. We want to find the point on the parabola that's closest to the point 1 comma 4. Closest in the sense that the distance is minimized, right? The distance d is minimized. All right. All right. Minimizing this means we're gonna talk about the derivative of this function d, and this function has square root in it, which is annoying to deal with. But remember the proposition we just proved? If you have a function which is non-negative, well, certainly this is non-negative, right? Certainly this is non-negative. It's the square root of something, so certainly this is non-negative. So if you have such a function on some interval, and we have it, the interval here is the y is minus infinity to plus infinity, right? Because this function blows up this way and blows down this way, right? Okay. So I is all of r. With x naught is an I, so that point is the desired point where the function is gonna reach its minimum. Well, the function d attains its minimum at a certain point if and only if the function d squared is attaining its minimum at that point. So instead of dealing with d, which has this umbrella in it, and it's annoying to handle, it's not impossible, it's just a little annoying, right? So it's a little convoluted, let's say. So how about we square this function and forget about the square root and find the minimum of the square function. Find the minimum of the squared function. And the good news is, by this proposition, once you find that minimum of the squared function, that's exactly the minimum of the current d function, right? So by squaring, we're not going to lose anything. It's just going to simplify the work that we're going to be doing. Make sense? So this is the use of that proposition that we just discussed. So by the proposition above, this is equivalent to, minimizing the function d squared. Correct? The function d squared. How about we call the function d squared by capital D? Okay. So what's d then? D of y, function of y, is simply that d squared, which means this expression without the umbrella. So 1/2 y squared minus 1 squared plus y minus 4 squared. Correct? Very good. All right, so we're gonna differentiate the function d as we've been doing before. We're gonna find the critical numbers for d, or of d, and as such, I'm gonna differentiate. How do you differentiate this? This is of the form function of y to some power. So this is power rule combined with the chain rule. So what do we get? We get 2 times 1/2 y squared minus 1 times the derivative of this function by the chain rule. What's the derivative of this function? It's 2 times half times y. And what's 2 times half times y? It's simply y. Plus the derivative of this, which means 2 times y minus 4 times the derivative of y minus 4 with respect to y. Obviously, I'm differentiating. So the derivative of y minus 4 with respect to y is 1. So this is technically times 1, but this means this, right? Okay. And let's simplify. If we simplify this, can we do it quickly? So 2 times half times y squared is y squared times the y is y cubed. Y cubed. 2 times negative 1 is negative 2, and negative 2 times y is negative 2y, plus the 2y, it's just doing algebra here, minus 8. Okay, and this means y cubed minus 8, right? This means y cubed minus 8. All right, so I don't have critical points coming from the first type, meaning points which have which allow d prime not to exist, where d is not differentiable, because look, d is everywhere differentiable, right? This is d prime. So the only type are going to be of type 2, which means where d prime is going to vanish. And d prime is going to vanish when what? When y is 2, right? So d prime of y is 0 if and only if y is 2. Because y cubed is 8 if and only if y is 2. Make sense? Correct. The other two roots are complex, so we're just dealing with the reals here. Okay. All right, so y is 2. By the way, how do you graph y8 minus 8? How do you graph this function, the cube function minus 8? Well, the cube function minus 8 is the cube function shifted down by 8, right? So it's the cube function shifted down by 8. So now what's the cube function? It has this form, right? This is the cube function, and we want to shift it down by 8, so we're going to take this function and shift it down by 8, and shift it down by 8. So something like this, right? Let's say. Okay, let's shift it up a little more. So something like this. So that's the point then. That's the point 8, negative 8. And that's the 2 we're talking about. You see it? It's right there. That's the 2 we're talking about. This is when this function crosses the x-axis. Okay? This is what? This is the function d prime. This is the function d prime. Right? So what can you say then? D prime is negative before 2. It's positive after 2, right? So d prime, the function d prime, I'm creating a small table of variations for d prime. D prime is negative before 2. Before 2. Why? Look, d prime, this is the function d prime. It's negative, it's below the x-axis before 2. It's 0 at 2. Function d prime crosses the x-axis at 2. And after 2 is positive, right? I mean, the assumption is that this keeps going, right? So at 2, after 2, the function turns into positive. So d prime is positive. And how does this translate to d? To d, this means the function is decreasing here, increasing here, right? So what is that guy then? It's a local minimum, right? It's a local minimum. But take a look. The function decreases and then increases and never comes back anymore. Never comes back anymore. So this is gonna be an absolute minimum, right? So it's an absolute minimum here, not only a local one. It's actually more than being local. This is actually an absolute one, a global one. Correct? So what can we say at this point? So D attains its global minimum when y is 2. When y is 2. So when the y coordinate of this generic point is 2. Make sense? So therefore the y-coordinate of the closest point is 2. Why? Because that's the point which allows d, the square of the distance function, to reach its minimum. Make sense? And we know that we discussed that it's equivalent, right? Whichever point that minimizes capital D is the same point that minimizes little d by the proposition we discussed above, right? Remember this? All right, so that's what I'm saying. The y-coordinate of that point that's closest, in the sense that d is minimum, that's closest to the green point 1 comma 4 is 2, right? So this guy is 2. The question is, what's x then? Well, we know how x and y are intertwined via this relationship. So if y is 2, now figure out what x is. So x is going to be half times y squared, and y is 2, so this is going to be half times 2 squared, which is going to be also 2. So the x and the y are going to be 2 in this case. Okay, so that would be the closest point to 1 comma 4, and that belongs to the curve y squared equals 2x. All right, so therefore the y-coordinate of the closest point is 2, and hence the x-coordinate of that point is given by, as we said, x equals half times y squared, which means half times 2 squared, which means 2. So at the end of the day, what's the point that we're talking about? It's 2 comma 2, right? So it's 2 comma 2. So all in all, the point in question is by point in question I mean the point which is closest to 1 comma 4, and that point belongs to the curve y squared equals 2x. That point happens to be 2 comma 2. All right, okay, so this is the end of this section.